Okay. Sorry for the interruption. All right. So the curl operator, right, completes the diagram in this natural way as illustrated by Stokes' curl theorem as follows. So if you take a line integral of a vector field over a boundary curve that's a boundary of a surface, just like this says right here, right? Line integral, vector field, curve that's a boundary of a surface. If you, on the other hand, take the flux of the curl of that vector field through the original surface, you get the same thing. Okay, so follows the pattern that we've seen. I think this is at least, let's see, I think it's probably our sixth time seeing this. Fundamental theorem of calculus, fundamental theorem of line integrals in 2 dimensions, fundamental theorem of line integrals in 3 dimensions, Green's theorem, Gauss's divergence theorem, and now Stokes' curl theorem. Okay. All right. We saw an example of this last time. I'm not going to go through the details of this calculation again, but the punchline, I was able to rewrite a line integral as a flux integral, and of course a necessary point there is that the curve over which I was doing the line integral is not just any random curve, but it's specifically a curve that's a boundary of some surface. And again, you can see that right here in the theorem, right? This theorem allows you to compute line integrals only if the line integral is, it says right there, a boundary of a surface, and you got to know that surface because that surface is your domain of your new flux. Oh. All right. So I'm going to show you one more example. Here's a vector field. Right. Now our curve is the intersection of that plane and that cylinder. Now you do have to do some geometry here, kind of figure out what is this curve, the intersection of that plane and that cylinder. So I've got them drawn over here, at least, some sense. There's the plane, there's the cylinder. And so this is our curve. And it's an ellipse, but it's not just an ellipse, it's an ellipse that's kind of tilted. Right, now I'll point out that what you could do, and again I'm not endorsing this, but I suppose you could do is you could parameterize this curve. This curve is pretty easy to parameterize. It's not that bad because you can just parameterize with x equals cosine t, y equals sine t, y equals sine t. Right, because the x and y coordinates are just going around the unit circle. That's not hard to parameterize. And notice that this tells me x is equal to z. Right, so you could parameterize that. You could take that parameterization and plug in and chapter 5 crank on this line integral. You can totally do that. So let me show you the alternative. It works out pretty nicely in this case. The alternative is to observe that this curve, this curve is a boundary. You can see it right there. It's the boundary of that disk. By the way, just a quick thought. I mean, it's the boundary of this disk. Sure, now it's also the boundary of other things. For example, it's also the boundary of, I don't know, if I wanted to take that half sphere, right? I suppose I could say it's the boundary of that. Or if I wanted to get weird, I could say it's the boundary of this, take a glove. Right, if you think about it, when you put your hand in a glove, the glove is a surface, and that surface has a boundary, and that boundary is the hole that you put your hand through. You could say, well, let's just take a glove and arrange it to where that hole is this surface. So this curve is the boundary of that surface, too. You can pick any surface you want. I encourage you to choose in such a way that it's to make your life easier, and don't pick a weird, wacky glove surface. And don't pick a hemisphere unless you have a really good reason to. Right? If you have the option to pick a flat surface, oh my gosh, yeah, certainly that's the best choice. Okay. All right. So since we are looking at, I should do that in green now. Since we are looking at a curve that is a boundary of a surface, right? can invoke Stokes' curl theorem like so. Okay. All right. By the way, I've completely ignored the question of orientations to this point. Let's go back and think about orientations. Note that our curve is oriented counterclockwise as seen from above. Side note, if you want to talk about the orientation of a closed curve in 3 space, you can't just say clockwise or counterclockwise, right? So, for example, here, look at what I'm doing with my fingers. Is my finger going around clockwise or counterclockwise? I say I'm going around clockwise. So it looks clockwise to me. Looks counterclockwise to y'all, right? So that's counterclockwise, but that looks clockwise. So you have to say as seen from where? From what perspective? So I'm saying if you're above this thing looking down on it, it would look counterclockwise. And so I note that that is the indicated orientation there. Yeah? Okay. So if that's the indicated orientation, then let's ask, well, what's the orientation then on this this surface here? Well, it has to be that way. And it's just a right-hand rule observation, right? I mean, it's the thumb, fingers, it's going to have it swirling around the correct direction. Whereas if you were to have done it the wrong way, if you were to have oriented this surface downward with what your fingers are doing, your fingers would be going around the wrong way. Okay, so there's our oriented surface. By the way, there's a typo here. Let me just correct the typo. That's divided by the square root of 2. Notice that I got this from looking at the coordinates, the coefficients, of the equation of the plane. That tells me what the coordinates of the normal vector are. Now, you might say, well, what about the minus sign? The coordinates are 1, 0, -1. Why did I put 1, 0, -1 here? Well, because that would be pointing the wrong way. You can tell it'd be pointing the wrong way because by inspection, this vector's got to be pointing up, up-ish, right? Not exactly up. And so therefore the third coordinate's got to be positive, and so you got to do that with the minus signs. All right, details. That said, we're now computing this flux, and it turns out this flux is really easy to compute. The curl, that's just a straight calculation. You take this vector field, plug it into there. Curl ends up being -1, -1, -1. No big deal, right? Just straight up calculation. And this flux is easy to compute because you notice that the curl and the normal vector that we noted above are orthogonal. Right? So dot product is 0. So I didn't have to do any integrals. Right? If you'd done this the other way, if you'd parameterized the curve, right, and gone off of this parameterization, you would have had to do an integral, and you would have sines and cosines in it. And it wouldn't have been a killer. It's just a pretty doable integral. I mean, the vector field's just got x's and y's and z's. The x prime would have sines and cosines. It's just doable. But I think this is easier. Everybody on board? Okay, there's another example here I'm going to let y'all read. The purpose of this example is to acknowledge, and if you look at this formula for curl, let's see, I'll go ahead and zoom in on this because I can. Look at this formula for curl. And you look at the third coordinate, and the third coordinate of the curl operator looks just exactly like Green's operator. Coincidence? Not a coincidence. So what I do in that example is I show that, in fact, if you use Stokes' curl theorem, apply it in a particular way to a curve and surface that are sitting inside of the xy plane in R3, but sitting inside of the xy plane as if it's R2, then Stokes' curl theorem turns exactly into Green's theorem. So you might say that Green's theorem, I don't want to say it follows from Stokes' curl theorem, but you can view it that way if you'd like. So not a coincidence. Okay. All right. Moving along. So how do we visualize curl? Is curl a density? As it turns out, not exactly. So this is a little bit of a discussion I have to give about densities. You remember we had this whole thing about densities where it seems a little weird to do so, but I encourage you to reinterpret the derivative as change density, because rise over run could be reinterpreted as the accumulating quantity of change per unit size. So quantity per unit size, that's a density. And it's great to think of it as a density because then you can interpret the fundamental theorem of calculus as being a statement about how the accumulating quantity of change actually accumulates. And the derivative points to where the accumulating quantity is and how much of the accumulating quantity is where. Right? It's very geometrically useful. And in that point of view on the derivative as a change density motivates thinking of divergence as flux density and Green's operator as circulation density. Right? So we spent a bunch of time talking about these points several days ago. So can you do this with curl? And what does curl look like? So it's a little bit different, as it turns out. I want to talk about this. Here's how the calculation would go for, I'm going to rewind and go to fundamental theorem of line integrals. I don't know if you noticed, but when we were rattling off these various boundary theorems, Gauss's divergence theorem, fundamental theorem of calculus, Green's theorem, they all behaved kind of the same way. And then why didn't we mention the fundamental theorem of line integrals in that same discussion? Is because it's a little different as follows. So here's the fundamental theorem of line integrals. We all know that. I'm going to follow the same pattern that we did in those previous discussions. I'm going to rename, the quantity on the left-hand side. I'm going to give that a name. I'm going to call it change, just like we did for the fundamental theorem of calculus. I'm going to rewrite dx as TDS. Right? So we have here then kind of an alternative version of, it's the same. It's just an alternative notation for fundamental theorem of line integrals. And here's the observation that change is just, an accumulation of little changes across the curve, whatever your curve is. And the fact that these two things are equal tells me that these two things are equal. And we have the opportunity to interpret something as a density. But it's not the gradient. Right, here's your density. Your density is gradient of f dot t. It's not just the gradient of f. It wouldn't make any sense to call the gradient a density if you think about it. Gradient's a vector. How can a vector be a density? That doesn't make sense. Okay? And furthermore, here's the thing that should all rights be interpreted as a density. This says change per unit size. Right? So if you want to say what plays the role of the derivative, but in the fundamental theorem of line integrals, it's arguably not the gradient, but gradient dot t. Okay, so what do we do with that? How do I visualize that? And what sense then can I make out of the gradient itself? It remains that I want to understand this thing, the gradient by itself. How do I think about it now? And so here's a picture I want to draw. Remember when we're talking about the fundamental theorem of line integrals, we're looking at some function. Hang on. There we go. I'm going to draw a bunch of level sets. And let's suppose that we are at that point. These being level sets, we know that the gradient is perpendicular to those level sets, right? This is gradient f. Okay. So where on this picture is the density? So keep my densities playing the role of a mass density. So there's quantity per unit size, so change per unit distance. Where on this picture do I see change per unit distance? The answer is I haven't drawn it yet. I can't really draw it yet because when you ask what is the change per unit distance, you have to say which direction are you going, right? If I'm at this point, as indicated, if I'm going that way, there's significant change per unit distance as I move in that direction. But if I'm going that way, I'm following a contour line. That's a level set. The function's hardly changing at all as I move in that direction. Right? So change per unit distance is not a scalar quantity. It's not a simple scalar quantity that I can just point to and say, oh, there it is. Right? Like if this was fundamental thermocalculus, it's just slope. That's it. Okay. All right. So it depends on the direction you're going. So let's suppose that we're going along a curve like that. Right? So I have this unit tangent vector. Well, but now I can talk about what the change density is. Change per unit distance as I'm going in that direction. Okay, now I know exactly what direction I'm going, and I can see how fast the function changes because of the gradient vector. Use the dot product, right? And so I can compute from what I have on the picture now of what the change density is. So what does that tell me about the gradient? Okay, there's lots of different directions you could be going. The gradient actually does tell you about a change density in a case. It tells you the gradient, by its magnitude, it tells you what the change per unit distance is in the optimal direction. Right? Old news, right? That's from chapter 4. So I point out then that the gradient's telling you two things. The gradient's telling you more than just what the change density is. The gradient's telling you, look, the change per unit distance as you move in the optimal direction is a certain quantity, and it tells you that by way of its magnitude. In addition, it's telling you what that optimal direction is. So it's giving you a density, in a sense, by what its magnitude is, and then it's also telling you what direction, so it's giving you what I call an orientation. What is the direction that change density is really honestly happening in? Right? And then you use the direction of the gradient vector by way of this dot product to see, okay, well, yeah, if you make some weird idea to go in a different direction, then this is how you adapt and get, as you experience it, how much change density are you actually seeing. Right? So the gradient vector is telling you two things. It's telling you the direction of change and how fast the change is going. Right. And so with that in mind, I like to think of the gradient then as being an oriented density. Oriented, telling you which direction the change per unit distance is, optimally. And by its magnitude, how much change per unit distance there is in that direction. So anyway, oriented density, kind of a weird construction, but very natural. You see how it comes up in the math. Right? Dot product of the gradient tells you exactly what your change density is. Okay, so the reason I like to start with the fundamental theorem of line integrals here, and applying this idea, understanding oriented densities in the context of the fundamental theorem of line integrals, is that this is more relatable. It's easier to draw pictures. Or you can visualize from personal experience, probably. The idea of walking up a hill, for example, and it's comfortable saying, well, yeah, there is a notion of uphill. I mean, uphill is hard to hike, right? And so if you walk off at some angle, you can viscerally relate to the idea, well, yeah, my altitude change, my change density, if you're on board yet with thinking of it that way, is less as you move off at some angle, and this is that formula. So it's relatable, it's easy to draw the pictures. And this sets up the mold or the template that we're going to use to understand curl. Right? So we're going to look at curl as relates to Stokes' curl theorem as being a total ripoff, total analogy of this picture. Instead of the fundamental theorem of line integrals and the gradient vector, we're going to be looking at Stokes' curl theorem and the curl vector. So let's go do that now. Let's see. In fact, maybe I'll just scroll like this. So here's the corresponding calculation. Here is Stokes' curl theorem. Right. curl theorem. We have a name for this object over here on the left-hand side. We call that circulation. Right, so I'm going to use sigma, lowercase Greek letter sigma, to represent it. So we have an accumulating quantity called circulation. It's computed with that formula. Well, yeah, but that circulation is also, if I just directly observe that it is an accumulating quantity, then I have that this is equal to that. And again, you notice we have this idea of the density being a dot product. The density is a dot product with the unit vector describing the orientation of your piece of your domain. Because the unit tangent vector, when you're talking about a little bitty piece of curve, tells you what direction you're going. That tells you how. Look, there's change happening, but the change is happening in this direction. You're kind of going the wrong direction, and this kind of accounts for that. Same deal with Stokes' curl theorem. There is circulation happening. This vector field is circulating. And curl kind of tells you how much circulation there is happening per unit area. But the curl is happening in a certain direction, and you have to do a dot product with your normal vector to see how much you're actually realizing that. Okay, so same idea then. The curl, it's not by itself a density. Density is a scalar. Curl is a vector, right? But the curl tells you two things. By way of its direction, it tells you how, in what direction is there a circulation. And by its magnitude, it tells you whether there's just a little bit of circulation or whether there's a lot of circulation. All right. So here's an example of how you can see that dot product actually realizing a circulation on a little piece of surface. Let's suppose I know the curl vector is this. And my assertion is that being the curl vector tells you that the vector field is kind of going around like that. Right-hand rule again. So the thumb in the direction of the curl vector, that your fingers will go around in the direction the vector field is circulating. And I'm going to draw that same picture over here now, same exact picture, same curl vector. Same circulation. This is just a different scenario, and I want to talk about two little pieces of surface. One oriented one way, and one same size piece of surface, but just oriented a different way, right? And let's talk about boundary circulation on these two little pieces of surface. Well, if you look at this piece of surface here, oriented like so. Right, the boundary curve is like that. And let's think about how much circulation of this vector field is there around this boundary curve. Well, there's a lot. The little boundary curve is a circle like this, right? The boundary curve's going around like that, and I'm asking how much is this vector field that's representing a fluid flowing around in exactly the same, my arms are going to get each other's way, but flowing around in exactly the same way, right? And that the curve is going, there's going to be a lot of flow of the fluid exactly along that boundary curve. So lots of sort of lining up, if you will, of the flow of the fluid and the direction of the boundary curve. And that coincides perfectly with how the curl vector and the normal vector are pointing in the same direction. So when you look at curl F dot n, they're going in the same direction. That dot product is going to be large. Okay, on the other hand now, let's consider this other scenario where we have the same sized piece of surface. If you want to, you can think of it, we're just going to take this piece of surface and just kind of tilt it a little bit, such that the orientation vector is like that. The boundary curve then being sort of like that. Right-hand rule. Okay, well, so how much, first of all, first question, how much is this fluid circulating around this boundary curve? Well, it's not really. I mean, look, there's a lot of circulation in the fluid, right? There's a lot of, the fluid's doing a lot of this, but to what extent is this circulating fluid going around this boundary curve? It's not. Right? As the fluid is going around like this, it's going sort of up on this side. Well, the curve is going this way. Right? As the curve goes around like that, the curve is going this way. When the fluid's going that way, they're not going the same direction. Right? And on the backside, as the fluid is flowing like this, on the backside, the fluid is going down, the curve is going that way. They don't line up. They're going completely different directions. So, just looking at the fluid and the boundary curve, you wouldn't expect there to be any significant circulation. Right? How the fluids flow lines up with the boundaries directions is, basically it doesn't. Okay, now how is that detected? How is that manifested by the normal vector? Well, the normal vector is pointing that way. The curl vector is pointing that way. There's not much dot product, if any, there. Right? So I think you can persuade yourself that the extent to which the normal vector lines up or doesn't line up with the curl vector is going to be coincidental, sort of simultaneous with how much is the direction that the fluid is kind of flowing going to line up with the direction that the boundary is going. So it works out very well. It's really a very similar picture to this one. Right? If you're going in the direction that the change is happening, right? If the direction of the curve is going in the same direction that the change is happening, then there's going to be a lot of change density, and that dot product will be large, and vice versa if it's a different direction. Okay, so strong analogy there. Again, here's the way you think about the curl vector. The curl vector. The magnitude of the curl vector tells you how much flow, how much is the fluid circulating, if you will. Right? And the direction of the curl vector tells you the axis around which the flow is circulating. Okay. All right. So that's how to think about curl. And so again, it's kind of a density. It's not really a density. It's an oriented density. But it's a lot like a density. Okay. There's a couple physics things I need to talk about. A lot of physics that comes up in vector calculus. By the way, I asked a professor in the engineering school one time, hey, what's the most important thing for y'all, for students to get out of multivariable calculus? And he says, well, the most important thing is the vector calculus. And the vector calculus is a sort of catch-all term that describes div, grad, curl, boundaries, this kind of, line integrals, flux integrals, that kind of stuff. The stuff we're doing now. Chapter 6, basically. The most important thing is vector calculus. Second most important thing, he says, is vector calculus. Third most important thing is vector calculus. So there's just it's so important. Vector calculus is crazy important in understanding lots of things. I mean, how magnetic fields and electric fields work it's the perfect, it's set up to be understood by vector calculus. So very important stuff. So I'm going to talk about magnetic fields just a little bit. So y'all probably remember, let's see, let me give myself a little space to draw a picture. I'll do it here. Y'all probably remember this from a physics class. if you have a charge, a current in a wire. So current flowing, so a bunch of charged particles, usually electrons, flowing in a wire. They talk about you have current in that direction. Awkwardly, electrons have negative charge, and so if the current is this way, what that really means is the electrons are going the other way. Oh well. Anyway, you don't need to worry about that. So anyway, you have a current going this direction, right? That creates a magnetic field. I don't know if you all knew that. If you didn't know it, no big deal. But it creates a magnetic field, and the magnetic field goes like this. It goes. This is going to be hard to draw. The magnetic field goes around using the right-hand rule. So if your thumb's in the direction of the current, right, then your fingers curl around in the direction that shows you which way the magnetic field lines go. Okay. So that's just how current and magnetic fields work. So I'm going to take that as a fact. This is empirical. Okay. So what's the relationship between the current in the wire and the magnetic field that it creates? And how can I write this down a little bit more precisely? So it turns out to be easier to write this down if you consider a more general scenario. So instead of having a current that's confined into a wire, common though that scenario is, let's suppose we actually have a flow of charged particles in space, like a fluid, ionized gas or something like that, right, flowing along. Well, this fluid flow is represented by J. We call it the current field. Current because this is a flow of a fluid, but it's a flow of a fluid of charged particles instead of just some regular fluid. Okay, so current field, J. Well, it creates a magnetic field, and not surprisingly, it's a magnetic field that looks a lot like what we just talked about. And kind of like that. So there's still a magnetic field that it creates, and there's still kind of a sort of a right-hand rule. Still a little bit hard to describe. Here's a wonderful fact. The magnetic field that's created by a current flow field, its curl is the current flow field. The current field. Oh, there's a constant stuck in here. The universe tends to do that. It just there are certain factors that just show up sometimes. So this is called the permeability of free space. It's just a number. Don't worry about it. So, other than that constant, the curl of the magnetic field is the current field. You can say this differently as a current field creates a magnetic field whose curl is that same current field. Okay, so this is another one of Maxwell's equations. Remember, we talked about two Maxwell's equations previously. The first two Maxwell's equations we talked about were about divergence. What's the divergence of an electric field? What's the divergence of a magnetic field? The second two are what's the curl of a magnetic field, and then the next one we're going to talk about in a minute is what's the curl of an electric field. So anyway, that's how that one works, and no surprise if you take this statement. See, if you take this statement here about the curl of the magnetic field being proportional to the flow field, the current field. And if you take a flux of both sides of that equation, well, check out what you have. Having taken a flux of both sides of the equation, Stokes' curl theorem now kicks in because I'm looking at a flux of a curl. Well, that's exactly what Stokes' curl theorem addresses. Flux of a curl is a circulation. Right? And on the right-hand side, what is the flux of a vector field representing a flow of a fluid. Let's think about that for a second. This is now the flow of a fluid. We defined flux in terms of thinking about the vector field as representing the flow of a fluid. And the definition that we came up with, our motivation for why are we writing down fluxes in the first place was if you have a field which is the flow of a fluid, like this one, flux says how much of that fluid is passing through the surface at any given point in time, per unit time. And we have a name for how many charged particles are going past a given point at a given time, and that's current. So this simplifies very nicely. And the punchline then is that these two equations, they don't look instantly like each other, right? But they're really very, very closely connected to each other. This is talking about the curl of a magnetic field. This is talking about circulation of a magnetic field. And by the way, just for semantical persuasion, this is about circulation. This is about circulation density. Okay, oriented circulation density, but still, this is the density object that we associate to circulation, and this is circulation. So you can see they're very closely connected to each other, and furthermore, the thing that makes it possible to connect them in the same way that Gauss's divergence theorem was the tool for the first two of Maxwell's equations, the thing that connects these two versions of the third Maxwell equation, Stokes' curl theorem. All right. A similar argument can be made about the curl of the electric field. I don't want to get lost into the physics because this isn't a physics class, and this is a really interesting discussion, and I hope you will look forward to hearing that discussion when you take Physics 152 or something along or one of your engineering classes on E&M. But we don't have time for you. By the way, this is one of the big ideas behind how electric generators work, right? In case that piques your interest. And electronic braking on hybrid cars works off of this idea. In a very fundamental and important way. So it's a super important fact. It's also one of Maxwell's equations. And you take this equation, and just like we did in the above case, take a flux of both sides. Now we're looking at a flux of a curl. Well, Stokes' curl theorem is set up to address that, so that gives you the circulation. And punchline, you end up with the integral version of this original statement. So again, here's a statement about circulation. This is a statement about circulation density. They look like different equations. We think of them, on the other hand, as being two versions of the same equation. Okay, so y'all have now all seen all four of Maxwell's equations from both different points of view. Again, this is not a physics class, so I don't expect you to really have perfect intuition about electric and magnetic fields. And by the way, I am leaving out a lot of stuff. This up here is only valid in the case that the flow of the fluid is steady state. That means that the flow of the fluid, the flow of the current field is both constant and there's no sort of accumulation of particles, like there's no charge buildup happening. Right? So steady state means there's no charge buildup, and furthermore, the flow is fixed, remaining constant. So it's a very particular case. And in that very special case, then you get this. And if you want to know what does Maxwell's equations look like in the case of a non-steady state flow, then life gets much more complicated, and we are not about to touch that in Math 212. Okay, so only steady state flows in Math 212. Okay, so moving along, we're now done with all of our boundary theorems. By the way, yeah, exactly. It's cause for celebration. I would like to go ahead and, now this is a couple pages forward. This is on page, where's my page numbers? 449, if you want to find are completed diagrams. Now, in fact, let me zoom out a notch or two here, so let's fit them both onto the page there. There's both of the diagrams. Here's our completed R2 diagram. Here's our completed R3 diagram. Well, almost completed. I am going to put some additional, there's a couple other neat things that I can write down that will supplement at the bottom of these, but we've made a lot of progress on our diagrams. And you see what we have then is a bunch of theorems. We have in these boxes the 5 new theorems that we've talked about that are all pretty much just shameless rip-offs of the fundamental theorem of calculus. Right? Fundamental theorem of line integrals, we agree. It's a rip-off of the fundamental theorem of calculus. Green's theorem. It's a dimension up, right? But it's morally, come on, it's the same pattern. It's pretty much a rip-off of the fundamental theorem of calculus, just in a very cleverly dimension higher sort of a sense. Well, likewise, Gauss's divergence theorem is just kind of a 3-dimensional version. And Stokes' curl theorem kind of fits in between in the sense that, well, it happens in R3, but it considers a 2-dimensional surface with a 1-dimensional boundary curve. They all follow the same pattern. And so just to illustrate that, I like to, at a time like this, so here's our R3 diagram, point out that if you look at what the fundamental theorem of line integral says, you take a curve, look at its boundary points, take a function, look at its gradient field. If you evaluate the function on the boundary points, if you evaluate the line integral of the gradient on the original curve, you get the same thing. And Stokes' curl theorem says the same thing. It's just one notch over on the diagram. Gauss's divergence theorem says the same thing, just one notch over on the diagram. Right? And likewise in 2 dimensions for Green's theorem. Okay, so I hope you'll spend a bunch of time with these diagrams. I think they're really helpful. By the way, these diagrams are not just something I just made up out of whole cloth. These diagrams are kind of do you remember I talked about how there's these more sophisticated objects that we can't talk about in Math 212? There's the generalized Stokes' theorem, and there's Theorem cohomology, and there's differential forms, and we just can't do that in Math 212. It wouldn't be appropriate. But a lot of that comes out of a large construction called chain complexes and cochain complexes. And what this diagram is, this part up here anyway, is really just kind of a pared down, rigor aside, should you think about it in 3-dimensional convenient context version of the corresponding chain complex and cochain complex. So this is a real thing, just kind of user-friendly version of it. So I hope you'll spend time thinking about these diagrams. If nothing else, I'm a big fan of analogies, and I think it's really helpful to, for example, if you're having trouble with, so there's a line integral happening here, curve. What curve? We were talking about a surface. What curve? Oh, well, we take the boundary of the surface. It's just like over here when we took the boundary points of the curve. Likewise here, we're taking the boundary curve of the surface. And likewise here, we're looking at the boundary surface of the 3-dimensional surface. Right? So whatever you understand about any one of these theorems, by analogy, you can help yourself understand that aspect of any of the other theorems. I think that's really valuable, and I hope y'all will spend a bunch of time with that. I'm going to do some stuff with that in the remaining half hour that we have here today. Okay. So I want to talk about this thing called path independence. There's fundamental theorem of line integrals. Y'all remember that. So I could apply the fundamental theorem of line integrals to that curve that has these 2 boundary points, x1 and x2. Right? So if I take a line integral of some gradient field, gradient f, whatever f is, some gradient field. The formula I'm going to get is f of that point minus f of that point. Well, here's the thing. What if I used this curve instead? C1 and C2. Well, C2 is a totally different curve. Completely different curve. It's a totally different line integral. I mean, that's hardly any of the points on C2 are the same as any of the points on C1. This would appear at a casual glance to be a completely different line integral, and yet, check it out. The value that we're going to get, well, the value we're going to get depends only on the starting point and the ending point. So the weird thing about this is, what that says is that the line integral, the value of the line integral seems to only depend on, well, where'd you start, where'd you end? It doesn't depend on the curve. It doesn't depend on the path that you take between the two endpoints. It only depends on the endpoints. Isn't that weird? It's almost kind of not believable. I mean, the picture that I had in my mind when I first saw this was, well, wait a second, how could this be possible? What if the vector field were to look like this? What if the vector field were really short up there? Right? And what if the vector field was just crazy long over here? I mean, the fact that these curves take place on totally different points, doesn't that mean there should be this huge flexibility of, well, the line integral up here could be small because the vector field in these totally different points is unrelated to the vector field over here where maybe the vector field's really long. And I mean, isn't this a counterexample? Right? Really big value of the line integral. Really small value of the line integral. How could they always be the same if they can clearly be different? This used to bug me. Right? And then I finally figured out that this is not a counterexample, actually, because the statement that we're making here, very critically, is only about gradient fields. If you want to cite the fundamental thermal line integrals, it is only a gradient field that you can talk about. Well, gradients, so that's a very special kind of vector field. We saw a while ago that lots of vector fields are not gradients of anything. And so here's the thing. This thing that I was hypothesizing, this vector field as well, it's really short over there and it's just monstrously long over here. That's not a gradient. So that's got nothing to do with what we're talking about here. Right? So let me emphasize that this thing that I said earlier about how, hey, line integrals only depend on the endpoints. Man, isn't that nice? Only for gradients, right? It's very, very important that we distinguish. It is only for gradient fields that we can make this statement that the value of the line integral only depends on the endpoints. Okay. All right. Now, to make it relatable, let's think about it this way. What if our vector field, what if our function f here, our little f, what if that little function f represents, let's say, altitude, just to have something to talk about. Right? If f is altitude, C1 and C2 are a couple of roads along which you might conceivably drive from your house to your friend's house. Right? Well, if f is altitude, then the line integral is keeping track of how much your altitude is changing along each step along the path and adding that up over the entire path. Right? This is a way of keeping track of how your altitude is changing and accumulating all the way along the curve. Well, the idea that we just talked about, how, wow, the integrals are always the same, how stunning. Really, all that says is it doesn't matter which way you drive from your house to your friend's house. The altitude change is always going to be the same. Well, of course, right? What could be more, I don't want to say obvious, but I mean, it better be, right? I mean, how much your altitude change is what's the altitude at your friend's house minus what's the altitude at your house. That's your altitude change, right? So It's pretty darn relatable, really. Think about it that way. So I want to talk about this, though, as being a property. Whether you view it as being extremely relatable or extremely counterintuitive, depending on the perspective you take, what we're talking about is a property of gradient fields. Gradient fields have this feature that it doesn't matter what path you take from your starting point to your ending point. All that matters is your starting point and your ending point. And the name that we give to this feature, this remarkable feature that gradient fields have, is path independence. And we write it down like this. I like to write it down like this. Gradient fields have this feature that the value of the line integral doesn't depend on which curve you pick, as long as those curves both start and end at the same points. So, gradient fields are all path independent. When we say that. Okay, here's a definition of path independence. I guess, I'll do it like this. So here's the definition of path independence. So I'm going to state this in general. Any vector field, whatever it might be, that has the feature that the value of the line integral is the same no matter what path you take, as long as they start and end at the same points, we'll say that vector field is path independent. Okay, so what we have up here, this is just the statement that gradients are all path independent. We have a gradient field, it's path independent. Because look, check it out. There it is. The gradient field has this feature that we're defining to be path independence. Okay. Everybody on board? So here's that result. If you have a gradient, that implies that it's path independent. And this kind of makes you really want to ask the question, does the arrow go the other way? I know that gradients are all path independent because the fundamental theorem of line integrals says so. But is every path independent vector field necessarily a gradient? Said differently, might there be other vector fields other than gradients? Yeah, it works for the gradients, fine, but maybe there's other kinds of vector fields. Maybe curl fields for reasons that we haven't thought through yet. Maybe they're all path independent. Right? It's a reasonable question. The answer is no. The arrow does go the other direction. And there's an argument I can show you for that, but I don't have time. Here's the statement though. If you have a path independent vector field, then it is a gradient. There is a function whose gradient is that path independent vector field, and you can read through the reasoning here. It's pretty straightforward. The punchline though is this arrow does go the other direction too. So among appropriately regular vector fields. And by the way, this is important. We really have to worry about. You remember how I mentioned that it's the fundamental theorem of calculus. If your function is undefined at a single point, then the fundamental theorem of calculus crashes and burns in a horrifying fire. Right? It does not hold if there is so much as a single point where something weird happens. Right? Very, very delicate theorem. And likewise for all the stuff that we're doing here in Chapter 6. Everything's got to be defined and continuous and differentiable. We cannot have any issues. So, as long as you have that everything's defined and continuous on our end, then gradients, path independent, same thing. Okay. All right, so a quick example. Let's suppose you have some vector field that's not really given, but you know certain things about it. And suppose you have this curve that's parameterized like so. So we have a curve, we have a vector field, and I want to compute a line integral. Well, let's go back to this vector field for a moment. I am not given very much information about this vector field. all I'm told is, well, there's these coordinate functions, P, Q, and R, and I don't know what Q is, and I don't know what R is. And all I know about the P coordinate function is that Z is a factor. So it's the coordinate Z times some function of X, Y, Z. That's extremely little information to know about this vector field. And I've been asked to compute a line integral of it, and it's tempting to say, well, I don't have nearly enough information to answer this question. But in fact, we do. We are going to be able to compute this line integral using path independence. Okay. And I am sorry, I have omitted to mention another thing that we're given, a key fact. We are told that this vector field is known to be a gradient. Sorry, that's important. Okay, so we know this vector field is a gradient. That means we know that our vector field is path independent. The fact that our vector field is path independent means that I can take this curve and just decide that, you know what, I don't like that curve. Path independence means I can pick any other curve that I want. Well, it starts and ends at the same point. I can pick any other curve that I want that just starts at the same place this curve starts and ends at the same place this curve ends. And it won't change the value of the line integral. The line integral will stay the same. So let's do that. Here's our, let's see, do I have a picture? I guess I don't have a picture here. Here's the scenario, though. If you look at where this curve starts when you plug in t equals 0. It ends when you plug in t equals 1. And this curve, therefore, starts, I should, hang on. This curve starts at the origin, and it ends at e, 0, 0. So our curve starts there and ends there. And what the curve looks like, of course, this curve is, it's some kind of wacky. All right, because look at the formula. It's got a 6th power in it, for crying out loud. Right, so I don't know what kind of crazy nonsense this thing does. That's approximately, let's say, what our curve is. But because we know that this vector field we're computing the line integral of is path independent, I can say, you know what, I don't like that path. And I think you'll agree with me. I don't think you like it either. Right? We don't like that path. I would like that path instead. Right? I mean, given the choice, you want to go do loop-the-loops with the 6th power, or do you want to just go in a straight line? Which would you rather deal with? It's a no-brainer, right? So let's take that path there. This path is super easy to parameterize, and all sorts of good things happen on that parameterization. So let's see, where did I write down the parameterization? Yeah, so here's the parameterization. T goes from 0 to 1. E times t, 0, 0. Super easy to parameterize. The derivative is easy to write down. There's our x prime of our new curve. Here's our vector field. Don't forget our vector field is this thing. And something really, really nice is about to happen here. This is where it kind of all comes together. This one little microscopic thing that we're given about this curve, the vector field, the fact that the first coordinate has z as a factor, ends up being tremendously valuable. This is a cool observation. Here it is. Check it out. This curve, I'll do this in purple. This curve, everywhere along this curve, z is 0. It's on the x-axis. Z is 0 everywhere on that curve. You can see it right down here in the parameterization that we made. Z is 0. And that means that in this integral here, that z is 0. So we're doing an integral of 0. The answer is 0, and we're done. Everybody see how that works? All right, now I have a confession to make. This example is, and I'm sure you've noticed this, this example is highly manufactured, right? Very, very manufactured. I mean, how often is it going to be the case that you have a vector field about which you know so terribly little in this weird way? And yeah, it's not very often. Right? So it's a manufactured example. There's a reason that I manufactured such a weird example. I'll talk about that in a little while. So here's another fact that you can. Well, actually, let me go ahead and talk about that now. I think this makes sense. So why did I manufacture such a weird example here to give you an application of path independence? So this thing is very strange. What's the point of this weird example? Well, here's what we already know. We already know that path independence is equivalent to being a gradient. So if we want to compute a line integral with path independence, any situation in which we could use path independence to compute the line integral, that vector field is a gradient, which means it has an anti-gradient, and that means you could use the fundamental theorem of line integrals. So who needs it? Then is a natural question to ask. Why do we care about path independence well, my gosh, the fundamental theorem of line integrals is it's a sledgehammer that crushes line integrals, right? So why do we need some other notion of that is simultaneous with it? So this manufactured example is one of those reasons. I can't use the fundamental theorem of line integrals here because I don't know what these coordinate functions are. I'd have to know what these components of the vector field are in order to be able to find the anti-gradient. So here I used the fact that it had an anti-gradient without ever actually finding the anti-gradient. So there's that. But there's a much better reason why we care about path independence. And that is, it directly relates to certain kinds of questions. So you may recall, I've talked about this in the past, but in Math 212, we're interested in more than just computing stuff, right? It's not just going to be compute this, compute that, compute the other thing. Right? What y'all are going to use multivariable calculus for in other contexts will not just be compute this, compute that, compute the other thing. I mean, Wolfram Alpha exists, right? I mean, so you need more than just hear how to compute stuff. Wolfram Alpha can already compute that stuff for you. Right? So path independence is actually a really important idea. And I want to talk a little bit about how it relates to physics. So there's another terminology for gradient fields. They're sometimes called conservative vector fields. Because it relates to conservation of energy. I want to talk through that a little bit. So y'all know about conservation of energy, and I don't mean in the ecological sense or like that. But conservation of energy is the idea that when you have something, let's say this pen, if I were to drop it, then it comes down here and lands in my hand. As it's going down here, it's moving fast. It's got kinetic energy. Where'd that kinetic energy come from? It didn't just appear out of nowhere, right? So where that kinetic energy came from was the potential energy that the pen had up here, right? Okay. So the idea of conservation of energy is that as something moves, if I take this pen and I throw it up into the air, as it moves, the total amount of energy that it has is constant. Right as I threw it, right as it lands, it has a lot of kinetic energy. A lot of movement, but it's low, doesn't have a lot of potential energy. When it's up here, it's not moving very fast, not a lot of kinetic energy, but it has a lot of potential energy. All right, so energy is conserved in that sense. Now, how would we define potential energy? Let's say at this point. Well, energy is what work is, right? So if I have something that's at this point, and if I move along a path there to that point, the amount of work that it takes to get there tells me how much potential energy the object has gained in going from there to there. Okay. So if I want to be able to talk about conservation of energy, I need to be able to talk about potential energy. And if I want to be able to talk about potential energy, I have to talk about the amount of energy that it takes to get from one point to another point. Here's the awkwardness. What if I went by way of that path instead? Right? The amount of potential energy that I give to something and going from here to there, it had better be the same amount of potential energy by this path as it is by that path. Otherwise, potential energy is not a well-defined thing. If I want to be able to say potential energy is a function of location, right, like height, right? To have any notion of potential energy at all, I need for the work along this path to always equal to the work along that path. We compute work with line integrals. So let me say that again. I need for the line integral on this path to be the same as the line integral on that path. In other words, I need for the gravitational field to be path independent. Right? Path independence is exactly the idea that you need in order to be able to define potential energy. Therefore, path independence is exactly the idea that you need to be able to talk about conservation of energy at all in the first place. So, anyway, a little bit of a physics aside, but that motivates the following terminology. These vector fields are sometimes called conservative because of how they relate to conservation of energy. Conservative vector field. Okay. Likewise, the function whose gradient is the vector field, so which, by the way, I like to call the anti-gradient. I love this term, anti-gradient. It's as honest and obvious, right? As what would make more sense to call an anti-gradient other than anti-gradient? It's the undoing of the gradient. It's the really, really natural terminology. So I call it anti-gradient. In other contexts, it's very often called the potential function, because that function is the function that talks about potential energy of the resulting vector field. Okay, so be aware of that terminology, especially in physics. They're going to talk about, instead of path independent, they'll very often say conservative, and instead of anti-gradient, they'll say potential function. Heads up. Okay, so I want to talk about how path independence relates to curl. There is a pretty neat connection, and it has to do with this picture up here. And I want to focus on this picture where we have a starting point and an ending point. I guess I'll do this. And I have a couple of paths. They go from the starting point to the ending point. And I'm going to appeal to your geometric intuition. You have a point here and a point there, and a couple of paths going from the same starting point to the same ending point. Notice there is a surface then that I can talk about in here. Whose boundary consists of those two curves. Yeah? Are you on board? Okay, sure, fine. Technically, these curves might go and tie themselves in knots in weird ways. It's not 100% clear that surface is going to exist. I'm going to assert that for reasons that we cannot get into in Math 212, as much as you think this might be a problem, turns out it's not a problem. So I'm just going to assert that. Don't worry about this issue. It's not an issue. If you pretend that this not issue doesn't ever create a problem, you're right. So anyway, let's just go ahead and assume that all of our pictures look like this. Okay. Now I'm going to observe that if I write down the boundary. Oops, I wanted to do this. Let's do this in black. If I were to write down the boundary of this surface S. It's tempting to write C1 plus C2. That's wrong. Keep in mind the boundary going this way, boundary's going around like that, it's C2 minus C1. And that minus sign is unfortunate, but it's there. Right on board? Some people like to point out here that, well, why don't we have C1 go the correct direction? Why don't we just have C1 go that way? Then we'd have C1 plus C2, right? That's more natural. The problem is, if you have C1 going the other way, then C1 and C2 no longer start and end at the same point. Right? We need for C1 and C2 to both start at the same point and end at the same point, and so you cannot just turn it around. Right? So this minus sign is going to be there. You can't get rid of it. It's part of how geometry works. It's not that. This is not an unfortunate choice of convention. This is a little bit of truth. It's there. Okay. Anyway. All right. So that being said, I'm going to now just write down Stokes' curl theorem as it applies to that picture. Here it is. Stokes' curl theorem. Of course, the boundary of S is C2 minus C1, as we just discussed. Right? And so I can rewrite this as that. There's Stokes' curl theorem as it applies to this picture. A flux through the surface of the curl of the vector field gives you the difference of these two line angles. Yeah?
But we went to the picture before.
Yep.
Can we just hypothetically think that you would start at zero and go with C1 and then minus C2? If we do that, partial Stokes is equal to C1 minus C2.
I think maybe I missed the first part of what you just said.
Because C1 and C2 point in the same direction, right?
Yep.
So can't we just do C1 minus C2 instead of C2?
So I, come to think of it, I really should have an orientation vector on here on the surface, and I'm going to say that the surface is oriented like that. Coming out of the page, if you will, and then right-hand rule means we got to go that way.
Okay.
Yeah, no, you're right, but I did need to have an orientation vector on there. It's an arbitrary picture, so it ends up not mattering, but you got a good point. Yeah. Okay, so it turns out this picture tells us wonderful things. This picture makes the following up, or this equation here makes the following observation. Let's consider what happens if the curl is equal to 0. Hypothetically, pretend. What if the curl of the vector field was 0? Well, then this flux would be 0, which means this difference would be 0, which would mean that this integral and this integral were always the same. Oh, wait a minute, that means path independent. Right? That's a crazy result. If you have a vector field whose curl is 0, that vector field is path independent. And the argument turns around backwards, too. Suppose you have a vector field that's path independent. Let's just say, hypothetically, path independent vector field. Well, draw a picture like the one we have above. Those two line integrals will always be the same. That means the difference will be 0. That means this flux will be 0. How's that possible? How could we have a vector field whose flux is always 0 no matter what surface you pick? The vector field has to be 0. So, again, assuming all regularity, no issues with points, things not defined, nothing like that. Path independence is simultaneous with the curl being 0. So we actually have then 3 equivalent things. So we already observed that gradient, a vector field is a gradient if and only if it's path independent. I talked about that at the start of this section. Now we see that a vector field is path independent if and only if the curl is equal to 0. So therefore, all 3 of these things are simultaneous. And again, everything has to be defined everywhere. No singularities or problem points, anything like that. Being a gradient, being path independent, having curl equal to 0, all simultaneous. So if you have any one of these properties, you have the other 2. Okay, and we're out of time. I will pick up here on tomorrow, Thursday. Okay, see y'all then.